Okay, so moving on. 14.7, today's section, tangent planes and linear approximation. And I think what I'll do is just at least get down the idea of tangent planes, and then maybe we'll do the approximation stuff right after break. That'll give you guys a little more time to look at that chapter 4 stuff too if you want. So there's kind of a big preamble here. They're talking about what does it mean for a calculus function to be differentiable. Okay? So in Calc 1, differentiable meant able to take the derivative, and it basically meant I have a smooth curve, no cusps. Because what happens is when you zoom in on a curve, it starts to look more and more like what? A line. Unless you're at a cusp. Unless you're at a cusp. I mean, I guess, you know, the picture is this, and if I zoom in, it's looking more and more like a line. That's what you call differentiable. Whereas, so this is differentiable. Not differentiable would be something that has a cusp, like the absolute value function. Because if you zoom in, what happens? That never goes away. Right? So this is kind of an idea of understanding what we want out of differentiability. We want that the linear approximation works if you're close to the point you're approximating at. That won't happen if you have something with a cusp. Okay? So if we want to extend our ideas today of linear approximation, we got to talk about what it means to be differentiable. And what we decide is that the best way is for the existence of what's called a tangent plane instead of a tangent line. Right? And so I have some surface, and I'm going to have some point, and I'm going to have a tangent plane. That's the picture we're going to have today. So, how do we get tangent planes to a surface? Answer: explicitly, implicitly defined. Okay, but here we go. If we want to take the derivative of something defined implicitly, f of x, y, z equals 0, this ends up kind of being the easiest way to do it. Okay, so let's slow down here. We've done two things, explicit and implicit. Here, let's do this. Let's compute the equation of a plane tangent to the unit sphere at the North Pole. Let's do that. Okay. Any way to start? What equations come to mind? Anything? A plane, okay. What's the equation of a plane?
Like the orthogonal vector component of the orthogonal vector times each component of the xyz plane.
So I noticed you said x, y, z. Yeah. X, y, z all have to be involved, right? And you could do it this way. You could say ax plus by plus cz equals some d. What Aaron is pointing out is that another way to think of this is to think of it as abc dot x, y, z. And so when you said you're thinking of a normal vector, right here, this is the normal vector. But remember, if I just write ax plus by equals d in Calc 1, you guys think, oh, that's a line. So this is just the generalization of a line. I'm adding one more variable. Of course, now we have the power of vectors to help us. What about the unit sphere, guys? That's right. X squared plus y squared plus z squared equals, yeah, since I said unit sphere, I'll say it equals 1. How's that? That's okay? And you might say, okay, so all I need to do is figure out where the critical value is. So explicitly, we could do this. We could solve for z. 1 minus x squared minus y squared, and then take the square root. And the rule is when I take the square root, I also have to put what out front? Plus or minus. But since it's north pole, that's why I said plus. Officially, you should say plus or minus, but north pole says plus. Right? And then, how do you compute, for example, the partial with respect to x? Bing, bing, bong. Yay or nay? Is that okay? So you get all this, right? So I guess it's negative x over the square root of 1 minus x squared minus y squared. Yeah? Is that too fast, or is that okay? You follow that? dz dy, I'm going to claim would be negative y over the same exact stuff because there's a lot of symmetry here, and so not much is going to be different. Okay. And we did this on the group work last week. We said let's find a critical value. And a critical value was either where these partials both equal what? 0, or where either partial was undefined. So let me write that next. Critical values at, well, the only way to get both of these to equal 0 is you need x to equal 0 and y to equal 0. Right? Or, where are the other critical values? I guess it's when you make the denominator 0. So let me solve that. The denominator is the square root of 1 minus x squared minus y squared, and we want to make that equal to 0. That would be other critical values. Well, if you square both sides and solve, you see that you're going to get critical values when x squared plus y squared equals what? 1. All right, so I'm going to sketch those critical values. The xy plane we tend to draw like this, right? So here's the x, here's the y, and then going up and down is the z. And so the critical values, there's a critical value right at 0, 0, and the rest of them are on the unit circle, right? Now what does the surface look like? Well, we know that that's basically the equator of my ball, right? And so when we say that 0, 0 is a critical value, you get a maximum there. You're going to get a tangent plane that's horizontal. What's the equation of that tangent plane, by the way?
That'd be like this is 0, 0, 1.
Yeah, 0, 0, 1 is the point. So what would be the equation of the plane?
So then x plus y plus z, which is z.
Isn't it just z equals 1, kind of?
Yeah.
Right? Well, but it's interesting because you guys were thinking of this, which is good. But let me point out, what is the normal vector to that plane? Well, for example, we could be using 0, 0, 1 dot xyz equals d. So we get z equals d, and it turns out that d is 1. You see that? So this is kind of explicitly how to compute the critical value. Oh, and what about the other critical values? Why are the other ones, the equator, critical values? Because what would be true about the tangent planes of anything on the equator? Well, they're vertical, right? And so you could argue that the slopes are somehow undefined there, in a way. Not that we're doing slopes anymore. Okay? But that's kind of interesting also. Okay. But maybe the easier way to do this is implicitly. Implicitly may be easier. So again, we had x squared plus y squared plus z squared was equal to 1. That was the equation we have. And so what we do, the idea of implicitly, is instead of writing z is a function of x and y, we will write big F of x, y, z is equal to 0. Instead of writing z as a function of x and y, we're going to write big F of x, y, z equals 0. So let me do that. I'm going to write x squared plus y squared plus z squared minus 1 is equal to 0. Here's my big F, x, y, z. Okay? And the point is that we can take a derivative. So the derivative with respect to, say, t, I'm just going to throw a new variable in there. I'm going to say x, y, and z are all functions of t. See this? And so if I say, what's the derivative of f of x, y, and z? Well, we get partial of f with respect to x times dx dt plus partial of f with respect to y times dy dt. Again, a single variable, so I can use straight d's for x, y, and z. I'm using curly d's because f is a multivariable function. Okay. And so the idea is that this is once again a dot product. What's it a dot product of? The gradient of big F, see that? Dot the derivative of x, y, and z. And so we say it's the gradient of f dot, and we've done this before, we call that r prime of t back in the last chapter, right? Because r was my position function. So here's the way to do it. The gradient vector comes back. It shows me how to get tangent planes. So, if we say, oh, one last thing. What did r prime of t tell you? This used to give me a tangent vector, right? And here we are dotting the tangent vector with the gradient vector, right? Well, if you dot them, and if you force them to equal 0, then these will be orthogonal. That's kind of the idea. So, they have a nice picture here, right? Where's my gradient? See the gradient? It's orthogonal to the tangent vector, this red one. Show the tangent plane. Let's do that. There's my tangent plane, right? So the gradient vector can be used as the normal. Doesn't matter where your which curve you're talking about. R of t could describe any curve going through that point. And it also doesn't really matter where P naught is, right? See how the gradient vector is always orthogonal to your... Okay, so now we have a much easier way of doing this problem in a way. All right. Implicitly, I define a new function of 3 variables, big F. I compute grad of big F. What is grad of big F? Remember, it's going to be a function of 3 variables. What's it going to be in our example? 2x, 2y, and 2z. Right? And so, we want grad f dot r prime of t to equal 0. Okay? So I want to be at the North Pole. So let's see. So we were, again, saying that there's another way to find the tangent plane at the North Pole, and that's implicit. Look how simple this is. We have the equation of the sphere. We take the gradient. Now, the equation of the tangent plane at the point ABC. Notice I didn't even use vector there. I said at a certain point is given by the following. Grad f dot, and I better make this big F. Again, it's thinking of it as a function of 3 variables, x, y, z. And then I'm going to write another 3-dimensional vector here, x minus a, y minus b, and z minus c. Set that equal to 0. Done. There's the equation of the tangent plane. So that's really kind of cool. Let's see it work for us. Well, in our example, what would we have? We have, so for the North Pole, we have 2x, 2y, 2z, right? Dot, I guess it's x minus 0, y minus 0, z minus 0 equals 0. No, not z minus 0, z minus 1. Okay. I better say one more thing. For this to work, we have to evaluate the gradient vector, because otherwise it looks like I'm going to get something quadratic here. So, let's take a peek. Yeah, you need to evaluate it at ABC. So, how am I going to say that? How about I say gradient of f evaluated at ABC? That's better. So for the North Pole, it's not 2x, 2y, 2z. We have that. We have the gradient of f. But what do we need to put in? Yeah, it would be 0, 0, and then when you plug a 1 in for the z there, you get 2. So 0, 0, 2, dot, this would be x, y, z minus 1 is equal to 0. So now when I dot these, I guess this is a very basic example. We get 0x plus 0y plus 2 times z minus 1 is equal to 0, right? So you just get that 2z minus 2 is 0. So again, simplified equation would be z equals 1. Which way is easier? Well, I said this is easier, but it did take me a few steps, right? But the big reason it can be easier is because sometimes it's really hard to solve for z. I mean, even in this problem, when I solved for z, you know how I needed to do plus or minus to get it right? But if it said z cubed, now you're taking cube roots. Or if it said cosine of z, now you're taking inverse I mean, you can make it really bad really fast. It's much easier to take derivatives sometimes than it is to solve for variables. And so this is our first example that I can think of where we made a problem easier by moving up a dimension. You guys, we had, the first technique was we're working in z as a function of x and y, two variables. We had to solve for z to get it that way. But you can make the problem easier by making it a function of three variables. Question, Aaron?
Yeah, I'm not sure how v of t is equal to x minus a, y minus b, z minus c.
Where are you looking at?
Well, the equation up there where you said orthogonal tangent vector. You know, the tangent
Yeah.
vector is v of t. But then you change the equation to x minus a. We never took a derivative with respect to t.
Yeah, so we would need an r. We would need a position function, right? And so how do we do that? That's a good point. They say here's v prime of t. dx dt, dy dt, dz dt. So I guess the question is maybe why is x minus a, y minus b, and z minus c what you need? Because it says the argument applies to all smooth curves on the surface passing through P naught. Okay. Yeah, but the question is, why do we have the x minus a, y minus b, z minus c? Let me get that.
You should be able to say v of t is equal to that.
Yeah. So let's see if I can do it for the sphere. I mean, we went through, or just any, but if I have some point here, right? A, B, C. And I say, okay, let me move somewhere else on the surface. So here's the point. Well, no, here's why. Here's why. Okay. We want x, y, and z to represent points. The combination x, y, z, we want that to be points on the tangent plane. So in general, x, y, z is some point somewhere on the plane. Okay? And so when I write this vector, x minus a, y minus b, z minus c, what is that? That's the vector starting at a, b, c and pointed to some random point on the plane, on the tangent plane, right? Or this one, or that one. All of these vectors could be represented in this way because ABC is a point on the plane. So the point is, take any one of these vectors and dot it with grad f. And we need big F. And we need, no matter which one of these I take, when I dot it with grad f, I get 0. So this is the picture. The point is, we're trying to define this tangent plane. How do I do it? I say, well, but for any point on that plane, there's some vector from ABC there. That's this vector. Does that make sense, Aaron?
It makes sense.
Okay. It's not the same as what I did here. Up here, I was just pointing out that, okay, it kind of makes sense from the chain rule that no matter what curve you have, r prime of t is going to show up dot with grad f. So this is kind of just motivation for why would you want to talk about grad f, this big function. But you're right, when it came to actually doing the plane, we just went ahead and did it. Yeah. That's a good point. Okay? All right. So I want to move on to linear approximation a little bit now that we have tangent planes. And then talk about differentials. Okay? So I guess first, they refer you back to kind of some ideas from chapter 4, and they're going to compare them to what you see now. And so here is their definition of what a linear approximation is. Notice they have L of xy. Okay, so I'll write it down. here. If z is some function of xy, we can define the linear approximation, just like we did in Calc 1, of f at the point AB in the following way, as follows. So, just like in Calc 1 where we had L of x, we're going to have L of xy. Okay? So this is going to be a tangent plane, just like in Calc 1 we had a tangent line. And now we know what tangent planes ought to look like. Okay? It's basically a gradient dotted with this x minus a, y minus b, right? So if you look what we have, there's the x minus a and the y minus b. Okay? So we're going to take Lx, I'm sorry, not L, fx, the partial derivative with respect to x, evaluated at AB. So this should be a lowercase f, guys. I got to be careful here. Let me write it below. Lowercase f of x, so the x partial derivative times x minus a, plus the y partial derivative evaluated at AB times y minus b, right? So right now you see that you could plug in anything you want for x and anything you want for y. What happens if you plug in AB? Well, then these go away. But if we plug in AB, we really want to be at f of AB, so we throw that there. Okay. And so again, this is the linear approximation. So f of xy will be approximately the same as L of xy if xy is close to what? AB. That's the point. This works if we're close to AB. Now, what do we mean close to AB? That's a good question. Here's x. Here's y. Somewhere here is the point AB. Maybe my linear approximation is good within some circle of AB. So that up in the cloud, in the surface, so what does the surface look like? I don't know. I could draw another hemisphere or something, right? Up here, there is a region on the surface where you would say that we know the tangent plane hits exactly at this point, right? So that's the point A, comma, B, comma, f of AB. We know that the tangent plane hits there, and as long as I'm within a certain distance of AB, we're going to say there's not a whole lot of error. There is some error, right? Because the side view, well, the side view looks like it did in Calc 1. You have this, and you have the tangent plane, right? And you have the surface. That's the side view, right? So there's some error. You guys with me? Now, how much error? Well, that's approximated by what's called the differential. Okay? So, just some notation here, okay? The actual error you might call delta f, right? How far away my linear approximation is from the actual value. Okay. But what we're going to get, and actually I don't like the picture I just drew. The reason I don't like it is because I feel like I should draw things vertically. That's the error, delta f. Okay. But we've defined linear approximation. What I also want to do is I want to define the differential. So the differential df is defined. Let me use the same notation your book does. Be smart. And then we'll go ahead and do an example. Yeah, they're going to, okay, so they're going to use dz, which I like. So, dz, let me show you that. So we're going to change the differential to be dz. So suppose z is a function of x and y. Okay, then the differential dz will be defined this. dz is the x partial derivative defined at AB times dx plus the y partial derivative AB times dy. And these are very small quantities. These are what we had as our Calc 1 differentials. So if you're reading there in Chapter 4, we defined those back in Calc 1. Okay? And so what I want to do is I want to show you how to use this. Let's use this to estimate some error. So here we go. Here's the problem. And do I need more room? Probably. Let's get more room. I'll do it here. Problem. Suppose the measurements of a box are, let's say, 10 centimeters by 12 centimeters by 15 centimeters. And we'll say that each correct to an accuracy, let's say 0.02 centimeters. That's pretty accurate, right? I can't do better than that with a ruler. I'm sure of that. Okay. So I have some high precision measuring. Is that high precision? 0.02? Depends what you're doing, right? I had these guys I used to teach linear algebra to a couple years ago. They worked for a company nearby that makes airplane parts. That wouldn't cut it. Let's put it that way. They had to be accurate to 6 decimal point precision when it came to, well, anyways. Okay, so here's the problem. Part A, I'm going to say use differentials to approximate the greatest possible error if the volume of this box is computed from these measurements. And then part B, I'm going to ask you this question. What, well, let's just say this. Approximate the percent error. On the volume. So, in some ways this is an easy example again because everyone knows the volume of a box is given by what? Sure, so it'd be x, y, z for our problem, right? So, you give this to any third grader and they're going to say, well, I can compute the volume, right? Because 10 times 15 is 150 times 12. What do we have, 1,800 centimeters cubed? Check me on that, guys. I don't do so well with third grade math. All right, I think that's where we're at. Now, what next? The exact difference, right? I guess we could compute, but we can do an approximation. It says use differentials. So the differential is going to be, well, dv is equal to the partial of v with respect to x well, that's not what I wrote, though, on the other page. I didn't use this notation, did I? How did I write it? I wrote it as, didn't I write it as Vx of AB? Isn't that what I wrote? So let's write it that way. Times dx plus Vy of AB dy plus Vz. Oh, and here's the thing, guys. I upped it a dimension without even kind of consulting you guys. It's not Vx of AB because volume's a function of how many variables? 3. So maybe I'll call it ABC. And what should be my ABC actually? What I really should be doing is here, ABC in this example equals what? That's right. Those are the values that we used to compute. So there's kind of two steps here. You want to compute the partial derivatives, and then you want to throw the numbers in, right? So how does this work? Well, what is Vx? Well, that means we're going to treat y and z as what? As constants. So you have a constant times x. So what's the derivative going to be? yz. Evaluated at, again, ABC. Times dx. Well, here, dx right? We know that each is correct to 0.02 centimeters. So I'm going to multiply it by 0.02 because that's my dx. That's the maximum possible error we might get. 2%. I'm sorry, 0.02 centimeters, not 2%. Plus. So here I'm going to have where it says Vy, xz evaluated at ABC, times 0.02, plus, and then Vz would be xy evaluated at ABC, bless you, times 0.02. All right. So moving on, looks to me like dv is going to equal, let's take this 0.802 and factor it out, because, well, it so happened that each was correct to the same amount. That won't always happen, but it did in this case. And so now where it says y times z, we can just do 12 times 15, right? 6 times 30 is 180, right? So maybe I should show where that's coming from. That's the 12 times 15. We're going to do x times z, so we're going to do 10 times 15, and we're also going to do x times y, which is the 10 times 12. So we get 0.02 times 180 plus 150 plus 120. So let's see, 330, 450. What's 2% of 450? Well, 1% of 450 would be 4.5, so 2% of 450 is 9. 9 what? This is dV, centimeters cubed. 9 centimeters cubed. That's how far off my volume might be. So I said it was 1800. Maybe it's 1791. That's worst case. Or 1809 is worst case. Right? Now it's interesting because we could actually compute the exact worst case scenario. This is not exact. This is a linear approximation, really. And I'll show you that next. But let's do part B and just see how bad this is. So part B said, what's the percent error on the volume? So I guess it would be 9 out of the 1800, right? And that's a low percentage, right? That's 0.5%, right? Because 18 out of 1800 would be 1%. So this is 0.5% error, okay? So that's how you use differentials. What if you had not known about differentials? Could you have still done the problem? Say you're in chemistry? Yeah, probably. What would you do? You'd say, okay, I know that maybe instead of 10, 12, 15, maybe it's 10.02 times 12.02 times 15.02. And you multiply those out. Right? What does that give me? That one I don't want to do without a calculator. So let me take one out, or you take one out, or someone. What do you have? 1809. Let's see. $10.02 times 12.02. I'm just trying to make this as bad as possible, right? Times 15.02. Enter. So, well, a little more than 18.09. But not much more, right? I mean, we said there might be a 9 centimeter. If you wanted to compute delta V, we computed dV was 9. Delta V, according to that calculation, would be 9.014 4, 8 is worst case. Okay? But you can see where the differential is good enough, right? So, again, as long as we're not off by very much, linear approximation works just fine. And this is an example of how it works. One other final thing maybe to say about differentials, okay, is that this idea here comes back. Because at some point, you guys are going to study something called differential what? Differential equations, right? So this is an example of what's called an exact differential equation, okay? Where you have a function of multivariables, it equals this. And this is something that gets studied in the future, and you'll say, oh yeah, we did differentials in Calc 3, I remember. So I just thought I'd point that out.